In the last video, we talked about the proof of work mechanism, which is used in a open model of the blockchain, particularly in the Bitcoin. And in this lecture, I'm going to discuss some possible attacks we have in the proof of work mechanism. Lots of the criticism on the proof of work related to environment, power consumption, and some successful attack which have been done on the proof of work. So let's start. Firstly, I would like to remind you that before this video, please see the previous video in which I have talked about the basic concept of proof of work. And for that, I have taken the hash case as a background so that you will have a real scenario that how proof of work mechanism works. So in hash case proof of work system, any miner can propose a new block only when he will give a proof of some work. That is, the proposed challenge by the network, the miner will have to solve first. And the winner of that challenge will be able to add a particular block. So definitely attacker will be discouraged because he have to work sufficiently large to some addition of blocks and for any changes in the existing block as well. He have to work. Now, suppose if we take the Bitcoin proof of work system again for difficulty, we can take this block hash mechanism. As you know that we have list of transaction in a particular block, some header information in the block, and in the header information we have previous block hash which work as a hash pointer to connect all the blocks, Markle root, and the block hash, the hash code of this block, and a nonce value. So if you remember that in the block hash, a message X is given and the hash code is also given. That is Y. So Y is given and hash function is known to you all. And we find out a value K so that X concatenation K, and if apply the hash function on this X concatenation K and we get Y. So here the same hash function can be used. This hash code is given and the message X you can understand like previous header and the Markle root. And now this N, that is nonce value, is at the place of that variable K. So how we can apply proof of work in the Bitcoin? Every time the miner will try to find out the random value N, that is a nonce, so that he will get the desired block hash. Say for example, the difficulty level is first 10 bits should be 0. So miner will try to pick a nonce value, a random value, and then compute the hash code. If the first 10 bit is 0, then he will be the winner. If it is not so, then he will randomly select another nonce value and then again he will compute the hash code. If he find the desired prefix of zeros, then it's okay. Otherwise, he will repeat the same process again and again. So in this way, this proof of work mechanism is used in Bitcoin network. Now, if we ask whether it is possible for an attacker to tamper this proof of work blockchain or not. So, as we know, this is the typical blockchain we have. Say we have 3 blocks in this slide. So we know that we have previous header. So this previous header works as a hash pointer and connect all the pointers. A timestamp, nonce value I talked about, Markel root. So if any attacker want to change, if he want to tamper this block, then he have to change all the blocks in the blockchain. So collectively, all the work done by all the miners to add all these blocks in the blockchain, he have to work all those work. Then only it will be possible for any modification in the blocks. And the current hardware configuration we have, it is difficult and nearly impossible to tamper this blockchain. Now, a certain attack we have. The first one is double spending problem. Double spending problem means using same fund again at the same time. Suppose you are transacting 5 Bitcoin to Bob and say Satya at the same time. If it is possible, then we will say that the attacker is able to spend same amount more than one time. So the solution we have, as I said, that in the blockchain, the transactions are irreversible, that you can't change the blocks with the hardware we have. So we can say that it is computationally impractical to modify the blocks. Every transaction can be validated against the existing block. So at the level of transaction also validation can be done. Next type of attack we have civil attack. Civil attack means there may be a group of attackers, they combine and make a group and collectively they can attack on the network. So attacker may attempt to fill the network with the clients under its control. And what can they do? They can refuse the relay of valid blocks. They can refuse to pass the valid blocks, and they will pass only their blocks, those blocks they want to be in the network, and that can lead a double spending, as I discussed. So a possible solution can be for that to diversify the connection. That means, say for example, a kind of subnet. Suppose we have a group of node, for that only one IP should be allowed. Only one IP for those group of network can be allowed. So it will diversify our connection, and which will avoid this type of attack. But again, the attacker may have the group of individuals from different locations as well. So the possibility of this attack is also remain. Next attack is denial of service attack. Suppose a attacker sending lots of the data on a particular peer or particular node, so that he becomes involved in processing of all those messages and not able to process the normal Bitcoin transaction. So normal Bitcoin transaction will not be possible for that, and definitely they can work on the desired target. So to avoid this type of attack, some solutions are, some guidelines are: avoid forwarding of orphan blocks, avoid the forwarding of double spend transactions, no forwarding of the same block or transaction again and again. We should avoid it. It can be avoided. If a particular node sending message, so too many messages again and again, we can remove. The network should disconnect or remove that node, particular node. The block size should be restricted to MBs. But here is one issue. Suppose if we have the block size very less, then we can avoid this type of attack. But the proof of work mechanism have a requirement of lots of the computational power. So if we will reduce the block size, then definitely proof of work mechanism will be used again and again. And if we increase the block size, then that computational power will not be required, or we can say it will be reduced. So we have advantage of having a large block size, but for this type of attack, to avoid this type of attack, we suggest for the lower block size. Now, as we know that, and as I said, but that it is computationally difficult to break the Bitcoin proof of work, but in future, it is possible. We cannot say that it is not impossible to break the blockchain, the Bitcoin PoW. So with the high computational power, high power server, in future it will be possible. And in 2013, there was a known double spending case. And this is the link you can explore if you want, that the GHASH.io mining pool was successful to complete the double spending. Next issue we have, that is monopoly. In proof of work mechanism, the miner needs lots of the computational power, and only those miner will be able to submit the block in the blockchain. Those will be succeed, those will be the winner of the challenge, and definitely for that a lots of the computational power is needed. So if you see the number of blocks, Bitcoin blocks available on public domain, you can see 5 to 10 are the major player. Those are, we can say they are dominating the network. So this is the important criticism we have for this PoW. Few miners with a large computing resources may get control over the network. So because of this type of monopoly, the user will get discouraged to join as the miner, and definitely miner will get less reward over time. Next, very important point here, that is the power consumption in the proof of work mechanism. As for the date on March 18, 2021, the annual power consumption of the Bitcoin network was estimated to be 129 terawatt hours. That is TWH. And if we compare the annual electricity consumption of a particular country with the population ratio, you can see in China, with this population, the annual TWH is 6,543. In United States, 3,989. all the data center worldwide 205, state of New York 161, and the Bitcoin network is 129 TWh. It is higher than the annual electricity consumption of Norway. It is double the annual electricity consumption of Bangladesh, and it is 10 times large the power consumption used by the Google, Facebook, and all. So we can see the lots of the power is consumed by this Bitcoin PoW mechanism. And definitely, personally, I feel that we should find out the alternative mechanism for this network. So in the next lecture, I will talk about the alternatives of this proof of work mechanism, that is the proof of stat and the proof of work mechanism. So enough for today. Thank you.